Well, hi, thanks for joining me here in my shop. Today is February 8th, and in front of me I've got a machine I didn't even know existed until a couple days ago, but here it is. This is a Transistor Radio Analyst, which means it's kind of a bench in a box for testing and troubleshooting small transistor radios out of the 60s, 1960s and that. But it could be used on any kind of transistor circuit. So I was having a look at this last night a little bit, just looking at the machine, when I suddenly noticed, oh my gosh, the pointer's missing on the meter. So I don't know what's going to happen here. I'm going to investigate that directly, right off the bat. The rest of the machine can wait until I know that this meter can work, and I'm sure I can get another pointer onto it, but does it work at all? How did a pointer break off? The classic way to break off a pointer, there's two ways. One is to drive the meter over so hard that it breaks. That's not terribly likely, especially with this unit. This is actually a vacuum tube voltmeter. There's vacuum tubes inside. There's two 1287s inside this guy. The other way is you have it apart and you're not watching, and you catch the pointer on your shirt sleeve and you break it off. Well, if you look at this guy here, these fingerprint smudges you can see are on the actual vacuum plate. They're not on the plastic here. They're right inside. So someone's been in there with dirty, greasy fingers, and I'm going to guess it's the shirt sleeve story. That's how it got broken. So what I want to find out right away is, does this meter work? This unit was in a shop being used right up until the late 90s, as far as I know, 1990s. So do I dare just plug it in and see what happens? I think to answer this question, yes, that's the appropriate route. No reason to worry about anything inside. I've got ways of turning things on safely, which I'm going to do. And we're going to find out if I can make this meter go up. Now, I would need some kind of test voltage or something to cause the meter to go up. And I'm not familiar with this device all that well yet. I've only just been reading through the very extensive manual that comes with this. Excellent manual that comes with it. So it does have a VTVM input here. You can set this to here. This is now a 15 volt full scale vacuum tube voltmeter. All I got to do is just hit it with a little bit of voltage here, and that should cause the meter to go up, and we'll find out if it works at all. I think that's really all there is to it. Everything else. So another possibility is that to put it on resistance, actually. Put it on ohms, and that should cause the meter to go all the way. Let's see. The ohm scale is at the top. Infinity is up here at the top. So I think if you just put this, come to think of it, just put it on ohms, the meter should go all the way up. The little tiny bit of meter here. Maybe that's all we got to do. Okay, so if we put this on ohms right now, some of these kinds of devices will actually have a battery in them. I've got vacuum tube voltmeters that have an actual 1.5 volt cell inside them to operate the ohms setting. Hopefully this one doesn't. Or if it does, it's still good. Let's see where we get with this. Okay, so I'm going to power this up with restrictions. If there's a short in it, we'll know by virtue of the light bulbs back here. How do you turn it on and off? Well, there's a good question. Where is there an on-off switch here? That's modulation off. This is RF turned off. Well, B, I don't see an on-off switch as such. Huh. off switch, where would I be? It would be right here. There's the off switch right there. So it's not off. Let's turn it off. Just to power up, first of all, see if there's anything really egregious with it. No. Okay, so I'm going to flip it on. When I do, I would expect to see one of these lights light up a little bit. See this one here. This one I believe is out. Okay, here we go. Okay, light lit up just a wee bit. So the indicator lights come on down here. Put it over to ohms. This hasn't moved a bit. There's an ohms, there's a 0 adjust here. VTDM ohms here. Oh, I saw some movement. Oh boy. Wow. I don't know, is that a good sign or a bad sign? Okay, we're running this only on 98 volts right now. Let's give it the full shot here. It's just staying up. Oh, did you see that thing jump that time? Okay. Okay, we saw what we saw. It's not good. Of course, this whole unit is based around this meter and the dial face on it. Oh boy. Let's take it out of its cabinet and just take a look inside. How to test a little transistor radio using this device. Lots of interesting ideas. Okay, I'm going to come out. What about the cord? The cord's kind of locked in there. Hopefully there's enough. I guess there has to be enough. Barely enough cord here. Well, it would seem to be the case that person to look back here. There we go. Okay. I did look at the schematic. There seem to be a lot of capacitors that might require replacement in here. 1, 2, 3, 4, 5, 6, 7. There's probably some small ones I'm not spotting. Then right on this circuit board there's a number of ceramic capacitors, probably okay. Let's see. Here's the meter right up here. It says calibrate for steel panel. There's probably some manufacturing information there. 4 screws coming from the front holding it. I didn't see any screws on the front. Looks like you have to pop off this plastic cover. That's probably how the fingerprints got on there. I'll expose the screws and off it'll come, but we don't need to take it off. We need to apply our own voltage here. Now I read this is a 1 microamp. I'm sorry, 1,000 microamp movement. I'm pretty sure that's what I read. Excuse me. So what we can do is remove one contact here and then apply our own voltage to it. Enough to get 1 microamp. Maybe we would do it on the other side of this resistor. This is a green, blue, black. So that's what, 50. What's blue? 8? 58? 59? What's the magic number there? 56. 56 ohms. That's better than nothing. So you can put some voltage here and here and watch the meter movement go. Not deep enough. First issue is the meter shot. Now, what low voltage supply have I got that will supply a low enough voltage? Maybe I got to get another resistor in here initially. Okay, let me get some leads. Okay, I've got it out. Got some leads attached to the back of the meter. We're going to try to power it up. Why has it gone like that? Seems to have fallen below 0 now. Okay. May go right over even if I just turn this on. Nothing happened. Okay, a little voltage to the meter. Nothing at all. Nothing at all. Not a thing. Let's put the leads the other way. This might be the end of the analyst right here. There. A little voltage. Oh my gosh, no, this meter works. Very good. Okay. 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 Dark clouds have gone away. We are in business here. And what business are we in? So this is an important device for me personally because I do get a lot of requests to repair transistorized stuff and small transistor radios too. And I reject them all because I don't have any real good experience at it. I'm busy doing the tube stuff anyway. And I didn't really have any way into learning about troubleshooting those small radios, which might sound like a small deal, and it probably is more or less. But with this device, I have a highway into learning how to troubleshoot those radios. I'm just looking everything over. This is a little odd. Going to a LED that's sitting down here, or a light of some sort sitting here, and this looks glued in. Not quite what a manufacturer would do. The glue is not too good in a manufacturing environment because it takes time. See, all these other things are held in with clips of a sort. So we have all these bigger capacitors. These are probably involved in particular tests and may not be involved in the operation of the machine under certain settings at all. might find that some of the functions work and some of them don't. What are the functions? Very briefly, it's upside down now. There's an oscillator in here with 2 bands on it. It can be modulated or not. It has a VTVM built into it, scaled in very particular ways, associated with doing transistor testing. You can hook up a transistor to these 3 clip leads, get it right, and test it that way. It does a leakage test through to see if the transistor is partially shorted. It has a beta test, measure the transistor's gain. Has some outputs here. It has a low impedance output for testing a speaker directly, higher impedance output for signal tracing, signal injection, and it has this is an audio signal, and this is an RF signal for doing that. It's a handy device. Has this rather unusual arrangement for supplying power to the radio under test. You just put one pin here in the zero spot, and the other pin in whatever voltage you want to run your radio on, up to 12 volts. Then this thing supplies the power for it, and that becomes an element of it being able to do some of the test functions. You have to power the radio from this device. Take a look at the circuit board here. The 2 tubes sitting here. Tuning capacitor for the oscillator, a number of resistors, some ceramic capacitors. There are no classic paper capacitors in here. This is probably okay. We don't know. Could have high resistors, could have leaky capacitors even though they're ceramic. It's just not very likely. What's far more likely is these guys are bad. This one's probably good. It's nicely sealed, but we don't know for sure. Likewise, this one down here is also likely good. Maybe the name of the game, the first stage here, is to replace all the most likely bad capacitors. This guy, this guy, this guy, this guy. 4 of them. Sure seemed from what little I did turning it on that it wasn't fully healthy. Problems could be anywhere, really. Should probably put the speeder back on before I forget. There are some calibration adjustments in it. Calibrating the oscillator. Could have some, there are some potentiometers here. They could be dirty. Switches could be dirty. Could be limiting the operation right there. I think the first step is to change out these capacitors. I think that's really what should be done. Good. Okay. That's good for a start. What about fixing the pointer? We'll worry about that in a bit. We don't need the pointer pointing to anything yet. Okay, well I have the entire instruction manual here, and I also have the schematic. Thank you very much, Pacific TV out on the west coast of Canada. They've developed a large collection of Canadian schematics and other stuff, all freely available. So thank you very much for taking the time to do that. Let's look at this schematic here. Now this isn't a radio, so when I look at this, it's as confusing as can be at the start. We'll start up here with the power supply. Zoom in a little bit. Still, there we go. So the power comes in. This probably simply travels to the on-off switch here. And that's it for the 120 volts. Everything else is on the other side of the transformer. 2 windings. This one, obviously this is the heater winding. It provides 12 volts AC at terminal A, wherever that is. Not sure where that is. If we look up here, you see 17 volts. So that's about 35 volts out of here, and then through 2 diodes, and I'm pretty sure this is a selenium rectifier I got a peek at when we were looking behind at the machine. Here's the filter capacitor, 500 microfarads, big one. Come down here, here's some more. And we have this power supply for the radio. Now they've got 10 ohm resistors. This is a 27, 10, 10, 10, 10, 10, 10, 10, 10. So I'm not going to try to study this enough to understand everything. I just want to be aware of the sort of the general operation of the machine. You're supposed to power the radio by attaching one supply terminal to this point, and then the other one you pick off here is the right voltage. Yeah, there's too many wires running around, too many lines in here for me to sort out rapidly, so I'm not going to worry about that. Yeah, all these switches make it very difficult to quickly understand a circuit. Switch 1A, B, C, and D. So the big switch number 1 has 4 wafers on it. There we see the meter. Looks like a diode protection. So if you apply too much voltage, the diode is going to leak it past the meter. 123, a 1% resistor here. Okay. Ohms adjust potentiometer. We have a output transformer here for supplying an audio signal right to the voice coil of a speaker in a radio under test. So you can check the speaker directly this way using this. There's all this coming from. Down here, okay. RF level control. Little capacitor here. PFD picofarad. That's the RF output. Pod is connected to the switch. Yeah, there's a on the RF level control. I believe if this switch is open, there's no modulation. Not sure of that. Audio output, audio level. Here we have audio oscillator. RF oscillator, vacuum tube, voltmeter bridge. So this is all part of the vacuum tube voltmeter operation. Components within dotted line are on printed circuit board. You can see the dotted line running around. Okay. There's a lot of resistors. Capacitor. Some trimmers on the tuning capacitor. Some switches here. RF oscillator. The audio oscillator is supposedly fixed at 2000 hertz. So both these capacitors must be related. Well, there's two bands, so that's probably what this is. There's two RF bands. That's probably why there's two capacitors. Oops. Just looking in there, yeah, it's a two-section capacitor. Both sections look identical in there. Both these sections. Now what about all these fairly large capacitors? Here's one down here. This one's on the board, supposedly. 175 volts. This is a 1 microfarad. Showing electrolytic with the curved plates. Is that what they're doing here? Here they've got the plus minus. They don't here. These are not electrolytic, but they have curved plates. In the diagram, here's one straight plates. So I'm not sure what they're getting at with that. It looked to me like there were a lot of electrolytic capacitors in there. Here's one over here, 0.1 curved plates. So I'd like to know, here's one definitely here. I'd like to know a little more about what the capacitors are I'm about to replace. 110 volts. 110 volts on the center tap. Plate. And then where's the other side? Whoops. Oops. Keep clicking my mouse buttons by accident. 120 volts. Not quite sure what they're up to here. So using this ground symbol. Open triangle. Is there any other ground symbols? Open triangle. Open triangle here. So does that mean to the case? Or does that mean to a common wire, common bus? There's the VTVM right here. Wait a minute. Oh, this is on the front panel. This is the input to the vacuum tube voltmeter. Whoops. Ooh. Wait a second. How did that happen? Let's try that again. How did I get out here? I started here. Go up. Under the correct setting. This will connect to this. Oh my. Okay, so there looks like 117 is brought into the machine to do some things. What would that be? I'm not sure. Okay, so I'm going to have to look at this quite a few times to really get a good grip on it. That's how this works. I have kind of a notion of what's in here now. Not a very good one. Probably good enough. There's nothing here that's telling me it's foolish to replace those bigger electrolytic capacitors. I would like this machine to be fully calibrated and operational. So let's read these notes. Resistors half watt. 10% unless otherwise specified. Capacitors in microfarads unless otherwise specified. Switches viewed from the front. That's important to know. switch 1, 2, 3, and 4. Showing you what position they're in. Black contacts without arrows are dummy lugs. Black contacts without arrows. So I think they're talking about this. Dummy lug. Why wouldn't they, a dummy word, why didn't they say unused? Because you have some here that are not black. Dummy. Maybe they knew I was going to read this. Position, selector switch positions. Last R is 15. No, the last R number is R39. Last C number is C17. It's interesting they put that. I've never seen that written on a schematic before. I guess it's just to keep you from looking for a resistor 40. So clearly we should go after this guy. 500, and these two are all related to the power supply. We really don't know the condition of the I mean, the unit could be completely operating aside from the meter, and I just didn't operate it correctly to realize that. But nevertheless, I think it's worth changing these. Find this one. Oops, tapers. So that's 1, 2, 3, 4. There ain't no more. Four of them. Whoops, why? My finger keeps, I got a heavy finger today. Okay, 4 electrolytic capacitors in there. The sizes are 500, 500, 500. Wow, okay, so there should be 3 that look pretty similar. 20. There was one more. 10, 20 and 10. So 2 small guys. Okay, let's go after these 500s. Do I even have a 525? I'm sure I do. 25 volt. They're all 3 that are 25 volt. Okay. That's the goal. Find those 3, change them out, stop clicking the button, and get busy. This looks pretty straightforward now. You easily see 3 identical capacitors. You can read on it 500 microfarads. There they are. Here's the replacements, these little tiny guys. Are they going to fit? You can probably get away with it, yeah. Okay, very good. I'm going to replace those. Actually, I'm going to take one out and we're going to test it. If I can do that right now. Why don't I do that? Keep the camera going. Okay, I'm going to preserve the leads, the lead wire. 525 WV. Okay. Throw the switch over to electrolytic. So we put the positive on the positive. So my experience with testing electrolytics is rather limited, in fact. Let's see what happens with this. Okay, so if you're looking at the eye here, you can see the open part at the bottom. I'm going to hit the switch. 50 volts going to charge up this capacitor. It's going to take a moment. The eye is going to close while the current flows. Then as the current stops, the eye will open. But if the current doesn't stop, the eye will remain closed to some degree. Here we go. Slowly opening. Well, that's not too bad. Electrolytic capacitors have a certain amount of leakage in them. That's why I'm not sure. I just don't have enough experience using this machine on electrolytics to say. Leave it like this. There's a short on the capacitor right now. We're going to discharge it. And we're going to test its capacitance. 500. Wow, that might just be a little high for this machine. 20 to 1,000. So we got a scale here it'll do it on. So we're going to adjust this until the eye closes. So this is giving me a very bad feeling. The eye is staying closed. I think that's a bad feeling. Well, it's most open around here. Pick a 20 to 1,000. It's right inside here. 20, so this would come out around just around 100 on here. Let's test it on another tester. What I found is when capacitors get leaky, these testers get unreliable. They report things that aren't actually valid. Let's try this tester though. This is a smart little machine. Let's see how smart it is. Okay, so it says it's a capacitor, it's 300 microfarads, the loss is 22%, and the effective series resistance 12 ohms. That just sounds bad to me all around. That sounds really bad. Let's just give a brand new one a test here. I'm going to put this on the other tester too. Okay, here we go. So 426 microfarads. It's supposed to be a 500. No, this is a 470. So it's testing at 430. V loss only 1.5%, and the ESR almost nothing. 0.25 ohm. Big difference there. Okay, I think we can condemn this. But let's put this on the other tester. Let's test the tester. These are new capacitors. There's nothing old about them. Before I charge it up, we'll do the. We'll try to read its capacitance here. Okay, so it opens biggest right about there. On the scale, we are just under 500 on the scale here. 500, 200, so just under means a fair bit under. So I think it's identical. I think the reading is identical. And we'll do the leak test. Here we go. Okay, it's charging up, very similar to the other capacitor. God, I just don't know what to make of that. So it hasn't opened all the way, because when I let go, you'll see the eye pops open further after discharge. There's no reason to think this is a bad capacitor at all. Just let it discharge here. A few minutes. There we go. I gotta remember, always turn this back to there. So when I go to test regular capacitors, I'm not fooled. Okay, I'm going to proceed. I'm going to proceed with replacing all three of these with three of these guys. Okay, so that's the three of them replaced here. That guy and those two guys in there. Now, we have another electrolytic here. And we have one up on the board here, which I think I want to change these two also. Then we can give this machine a bit of a test for real. So this one will be easy. This one, let's see if I can get it out of here. The negative, looks like the negative post is this way. See if we can just pop it out. There we go. Negative, positive. So negative towards the front. 10 microfarads, 175 volts. Okay. 10 at 175. Let's find one of those. Okay, here's the replacement. This is a 10 at 400 volts. That's the closest I can do. That's fine though. 10 at 175. Let's just give it a test on here and see what this says about it. Okay, so 9,000 nanofarads would be 10 microfarads, I think. ESR 19 ohms. One here. Similar 8700 nanofarads. ESR 4.4 ohms. It's about the same. P loss is much lower, 0.8. Okay, so I have a lot more faith in this than I do in the original one, which certainly looks old to me. I'll put this one in now. Okay, that one's in. That leaves us with this one here. Positive going to the little transformer. Let's stick it on the tester. 20 at 150. 20. Da da da. 25. So it's reading high. 6 ohms, 3.6. Well, interesting information. I'm not exactly sure how to interpret it. 25. Probably indicating this is leaking, and it's causing this to give a false indication of a higher capacity than what's there. 20 at 150. Okay, I'll hunt one down and stick it in there. Okay, so that's the 20 installed here, and the clearance there. There we go. Okay, so that leaves 3 fair size non-electrolytic, 1, 2, and 3. I'll leave them there for now. But, these larger electrolytic ones are probably responsible for filtering things, and a significant difference. So I'm just going to put this in with 1 or 2 screws. So, we're going to give this guy a try. see if it really operates. Okay, so how are we going to know if this is working at all? I think the easiest way is to set it up to produce an RF signal and then try to tune it in with a radio. I happen to have one right here. And we'll try that. There's quite a few functions in here, so maybe one function is going to work, others aren't. But let's start with this one. This is my. So this has a loop antenna in it. That may be a little tricky, but hopefully there's enough RF coming out of here. Let's try this little lead here. Okay. And I'm just going to kind of hold this near the radio and see if it doesn't pick it up. That's my plan. Put this on leakage for some unnecessary reason. The other settings are in circuit meter set. So this is for adjusting the meter when you're doing an in-circuit test. This is set to in-circuit. We don't want it there. We want it. Where do we want it? We would probably want it on this 15 milliamp setting. The setting here, 15 milliamps, is the draw from here. Now I noticed the light, it looks like an LED that was installed. It's obviously well, it's interesting. This B-2 here. I think somebody did this. I think they removed this B-2. So that's for a transistor with 4 leads, 2 base leads. I don't know if I've ever even seen that. So I think they removed it, stuck their light there because there's no indication the unit is on or off. I think that's, unless you look up at the knob. So they wanted a light here, I think. And they just hooked this up to one of these. Now this is a bit of a problem because the instrument is sensitive to the current draw from what is supposed to be the radio supply. We'll ignore all that for now though. So audio and RF level, I think that would be minimum and this would be maximum. Go a little bit further, the modulation turns off. We'll keep the modulation on. Maybe it's there, and then we got this setting up here. What's going on with that? The pointers are not moving. Oh, there they go. Okay, so the pointers they have a mind of their own here. Now there appears to be a pointer right on the dial. Yeah, there's a pointer marked right on the dial, so we don't have to worry about these guys. To start with, we want to be on band B, 800, 900, 2000, doesn't sound right. 250 to 800, with 455 marked. Well, so it's what's got it's got from 250 to 800 and from 800 to 2000, which must be must be 2000 kilohertz or 2 megahertz. So if we're going to be in the range of the radio, maybe put this up around, why don't we use band B, and we'll set it around, say, 900. This would be around 900. We'll start there. Put the radio on. It's right around 900. Let's get off the station here. Up to 900. Precision doesn't matter, but why not? Okay, 900. We're ready. We're ready for what's going to happen here. Let's plug it in. Now I certainly have a chance to have introduced an error, so I do have the dim bulbs in the circuit. Let's just switch to 15 milliamps. There we go. A little light came on. Oh, and I'm getting a phone call. Wouldn't you know it? Okay, I was out of the room for quite a while. I turned this on and walked out of the shop. What a mistake. What a mistake. But the fellow I just talked to wanted me to fix his 1970s car radio. I get a lot of calls like that, and I say no to all of them. No car radios, no transistorized car radios. Okay, where are we at now? So no smoke came out of this. In the meantime, even though I wasn't in the room, shame on me. We're running with 96 volts. Let's put it up to the full Monty here, 113 volts. Let's turn up the radio. Put the RF near the antenna. What do we get from this? I don't know. Okay, so nada at this point. Oh, RF off. So we want it on band B. There it is. Pretty weak, but the way I'm doing it is not the way it's intended to be used. So it's at 900, and this thing is pointing pretty much at 900. Oh, diggity dog. Let's try this other band. I'll dial in 600 here. Okay, we'll go to band A. I can hear a tone somewhere. It's gone. Now 600, so 600 would be over here. There it is. Now there's other noise signals in here, so that's why it's got that funny chirpy sound. Modulation on and off, or level. Now I'm going to clip it to this. This is actually the FM antenna input for this radio. But it'll get the signal further into the radio. There we go. So you can see the AVC quieted down the radio. Where's the modulation? Where is the modulation? Doesn't appear to be any modulation. Maybe I don't know what I'm doing yet. There should be a 2 kilohertz tone there. So there's an audio output which produces the 2 kilohertz tone. And we also have this voice coil that will drive the speaker directly. Why don't we experiment with those next? What about all these settings? They aren't going to do anything. This is just controlling the meter settings. We'll get to that in a minute. So let's see if there's any audio coming out of there. How would we do this? Well, so to use the voice coil technique, you have to have a lead into the negative here of the VTVM and the voice coil. So you can easily get into here. No, I'll turn this off. I need a speaker to experiment with. Okay. Grab one here. This guy here. I can stick these wires right in. So I think this would be the level. I'm going to turn it down. Wire here. Okay, maybe we'll use. It's not very good. So some of these, maybe they've had a larger stuck in there. Okay, let's go for direct wires. Don't know how loud this might be. Nothing. We need to prove this speaker is working. Wires are in the back. So a crude way to test that would be to grab any old battery. We don't know if the battery's good, but we'll know in a moment. Yeah. So it appears as if the 2 kilohertz component here is missing, because we've missed it twice now. Audio output side of it would have to go into some kind of amplifier or something for us to hear it. I think we can pretty much bet that it's not working. Is there some other control I didn't have in the right place? Don't think so. What more can we test on this? We can hook up a transistor to these and perform a transistor test. Okay, why don't we try that? It's a bit of a clumsy looking leads there, but I think we can get away with something here. I'll find a transistor to test. Okay, so I picked this one here. It's never been in a circuit. It's brand new. And this is a T2955. It's a power transistor. With this great little tester here, they don't even have to be concerned about base emitter or collector. It figures it out for itself. It's good. It's going to tell me, in fact, base emitter collector. So when I go to connect it here, I can do it properly too. So, what do you say? You say beta 71. The voltage drop through is 578 millivolts, a little low, but I don't think it matters. And the leakage current, I think that's what it's showing here, is leakage current 0, 0. So I think we're really good on this. This is a good transistor. Now, who's who? So looking at it from the front, it shows it's gone. You gotta move fast with this guy. Let's try it again. Wow, we got these arranged. So I've got 1 into 1, 2, I've got 1, 2, 3. Okay, so what are they? 1, 2, 3. Let's let it test it again. Puts a nice little diagram here. 1 is the base. Base. 2 is the emitter. Emitter. So base, collector, emitter. Base, collector, emitter. Okay, base, collector, emitter. Am I going to remember that? No. Base, collector, emitter. It's actually in the order of the alphabet, B, C, E. Okay, now I'm going to have to stop and read up a little bit on this guy, figure out how to hook these up properly. Oh, it says right here. It says right here. But I need to have this in the right, no, oh, I didn't notice. Is it NPN or PNP? Well, apparently you can hook this guy up, and if you have this set wrong, an NPN or PNP switch, you'll quickly figure that out, no harm done. Supposedly. So we have a leakage and a beta. Beta was 70, was it, on there? And we have a meter with no pointer anyway. So this would be transistor check, out of circuit, in circuit. That's a very clever device. Like this guy, test components, very clever. This guy tests a radio. Clever use of this. Get you a long ways, which is why I'm a little excited about this guy and his extensive manual. Okay, so I'm going to read up and we'll find out what we can do with this guy. Okay, so I've read the section on how to test a transistor out of circuit. So this is set to out of circuit. This is set to PNP to start on leakage. Leakage is between the collector and the emitter. We have another technique for determining if there's base to emitter leakage. So we take the base wire first, clip it on. Base, collector, emitter. Next one would be the collector, which is the red one here. There's no push to test button, is there? And this last one is the collector. There we go. She's hooked up. What's supposed to happen now? The meter's supposed to be reading already? So it says if you get no reading on the leakage test or the beta test, look at that. 30 switches. Okay, that's something we gotta take care of for sure. It's gone way up. So you can read things directly, like for instance the beta can be read directly. I think it's 150 at the top, so this is suggesting under this arrangement we're getting a beta of 140, which is quite high. Leakage is showing, I interpret this to mean nothing. What if we flip it over to NPN? Now we get nothing. Okay, so we don't. It's definitely a PNP according to what I'm doing here. No leakage. So we look in the leak. There's a leak band, and then there's the beta band, and you can see good, questionable, bad. Up here is bad, questionable, good, questionable, bad. So on the leakage test, we're in the good zone. This little extra green part, you can see the meter just touching. This has to do with testing the transistors in the circuit, which is a very interesting thing that they do with this. And there's a setting I believe you set this to get this in the green zone. Then you perform the test and watch what happens after that. So we look at the good and the bad. On the leakage test, we're in the good. On the beta test, we're in the bad. We're in the bad. Now the other machine indicated 70. So somewhere around here, but the pointer's pointing way up here. Well, who do you believe? The idea here is if the beta number is crazy high, like 140, 130, and that probably indicates a leak through the base to emitter, I believe. Well, we're getting action anyway. That's good. It seems to be working. What the leakage is nothing. I mean, this is a brand new, never been used, not brand new, NOS transistor. This could go right back to when I was in college. This is a little pile of junk I've been dragging around since I was in college. Collected little odds and ends. There's a whole bunch of them here. I'm going to take a little tiny, let's take a little tiny one like this. Regular signal one. Never been installed. I'll do it on the computer. There is a hum that comes out of this. Maybe you can barely hear it. It's a tone from the cabinet vibrating. I don't think it's 2,000 hertz though. Okay, and what do you say? Yeah, that was pretty quick. So beta 171. Wow, way up there. Voltage drop almost 700 millivolts. No leak. 1, 2, 3. Collector, emitter, base. Collector, emitter, base. Okay, we got it. Collector, emitter, base. So we take the collector and follow number 1. Number 2, emitter, base. Emitter. Number 2 is the emitter. Base goes here. That's really pretty likely to get a short in there. Oh, see the meter jump over there? I hate spreading out the leads, but that's what I have to do. Okay, so there we are. We're on. Oh, what did this say? Was it NPN or PNP? I don't know. So we see what the beta is. Oh, big beta number. Right over. Okay, try the same thing on this setting. We get nothing. So it's at PNP. And the beta stops at 150. That thing measured it at 171. Okay. And leakage. Apparently that's where the 0 is. Let's see if we can zero this a little better. Could be this right here. this may not be mechanically connected to the movement. If somebody takes the plastic case off, there's a challenge putting it back on, getting a little pin to go into something, and it may be that it didn't go in. See, it's not moving the movement at all. So I'm going to guess this is disengaged from the meter movement. Can we see it? I'm looking right inside here. Eventually it'll probably bump into it. Yeah, it's bumping into it there. Oh, it's moving it now. Not much though. Yeah, I'm not sure if it's engaged or not. And it could be that this is, whatever happened to the pointer, we don't know. Did it get bent? We don't know. So what have we got? So we appear to have the transistor testing function functioning. Okay, we can test the VTVM now. So we need to put in a lead. Okay, these are all weak. Let's put this over on 15 volts. Oh, this just dropped. Okay. So maybe it doesn't go right to 0 when you're on this setting. Not sure what's happening there. Okay, that's why we're testing everything. I need a little voltage source here. That's gain. Okay. This is in the plus. Let's put this in the negative. Very loose. Very loose. Let me just try something here. Where's the drawer? There it is. Right here. Oh, those are way too big. They're not going anywhere. How about this guy? All loose. So I think these have just gotten loose. Loosened up. Okay, well, we'll just do our best here. So we'll put that in the negative, and we'll hook up the negative here. And the positive, what can we use? We can try this. Yeah, very loose. Okay. So once this is on 15 volts, this is a voltmeter, and these are the input leads. And I have these backwards. Duh. How did I manage that? So it says in the instructions in quite a few places you cannot harm this meter because it has a limiter on it, limiting diode, and it's a VTVM too, so it's not direct to the circuit. So we're gonna, here we go. Okay, now we're going up. We're going up 10 volts. This should be up at 10 volts. We should be up. I guess you just read it off the 1.5 scale. 10 volts would be here. Didn't move. Not moving. Somewhere on here. Okay, so we have this right. This is for setting the green patch. This is the ohms adjustment. This is the output. I should turn RF off probably. I have the feeling the VTVM is not working as a VTVM. Is there any reason why this wouldn't have voltage on it? There's no reason at all. 0 happening. Okay, so I'm going to turn this down a little bit to around 5. Ooh, way down to about 1. On scale. Nothing happening there. looks like the VTVM, I'll give it some more juice. Oh, it's moving. You see the pointer move a little bit? But I'm cranking it way up. Well, way up is 10 volts. Okay, so there's something happening, not what we want. But there is something happening. Okay, something else we can look at now. How about these supply voltages here? Are they, these ones here, are they in any way accurate? So we'll check that very simply. Because using these is a major part of getting this thing to function in a good way. Okay. This meter, 20 volts, full scale if it matters, 0. Let's start with, well, there isn't a 10, we'll start with 9. Wow, that's pretty sad. How can this light come on? 7. No, come on, this meter's not doing things right. Let's try again. 0, 9, 12. Okay, so what's 12? 14. Now, supply voltage is 113. It's not even full on. If we put the supply voltage up to where it should be, 117. Here we are, 117. You got almost 15 volts on the 12. Hey, it works better than it was intended. Okay, it wants to test them all. 1.5 volts. Yowza. Now there's no load on this, so maybe that's part of the deal here. This is expecting a load from the radio, small load from the radio. Why are you jumping around like that? Negative is right, so that's double. It's supposed to be 3, it's reading 6. 6. Not double, but lots. So there's a string of resistors in here that's controlling the voltages. It could be trouble in those resistors. But it does produce power. So if we knew how much this is by taking a reading, we could use it. Like you could put that in for 6 volts. Okay. There's a whole bunch of 10 ohm resistors in there, if I remember right. What's left that we can check quickly here? Nothing really. So we found audio output not happening, 2000 cycle modulation not happening, so that part of the oscillator is not working at all. We found RF seemed to be okay coming out of it. So the RF side seems to be working, the lower audio side does not seem to be working. Transistor checker appears to work. VTVM does not appear to work. Appears to work very, very little. Okay, well I think that's all the challenges. I'm going to have to study up on the schematic, try to figure out what area might be in trouble, and what it is I can do about it. It's possible one of those tubes, or both of them, have trouble in them. We should test those. Maybe that's how I'll end the video today. I'll test those 2 tubes, and that'll be the end of it. Okay, I've got this set for a 12 AU7. This is definitely a 12 AU7. Let's just double check everything here. Make sure I'm not doing something wrong. 12 AU7. So the filament is set to 6 volts, not 12. So this is probably a center tapped 12 volt filament. So with a center tap you can actually power this guy up with with 6 volts. to each. There's probably 2 heaters in here. Signal level 2, 18H, PGK77, PGK77, 3516, 3516, 29 on the cheater, F for the plate. So it says rejected at 710. So 710 is around here. Okay, in goes the first one. Okay, you can see both heaters coming on. Yeah, there's 2 separate heaters in here. So you can run them in series or in parallel. Here we're doing this in parallel with the 6 volt setting. Okay, we'll check to see if there's any shorts inside the tube. You'd expect the meter to come up if there was. Nothing there. Okay, so this is testing one of 2 sections in the tube. Right, 710, right about there. Here we go. Oh, it's right on the fringe. Okay, now we'll do the other half of the tube, and we simply get there by flipping the PGK switches. Okay, and run the test again. Not so good. Not so good. Okay, this guy, not so good. I'll get the other one out. Now, is it so bad that it would prevent that machine from working? Well, it would make certain outputs weak. So one of these is driving the VTDM and the other is driving the oscillators, if I remember right. Okay, check for shorts. Nothing shorted. Okay, we're starting with the one half of the tube. Oh, worn out. So none of it reaches the reject point. Let's check again. The reject point is 710. So this is measuring 450. 710 is up here. That's the reject point. You really want it to be up in here. So both these tubes have tested very weak. It probably indicates that this instrument was left on a lot. And the cathodes are worn out. Probably the case. I gotta get a couple of 12AU7s. A couple of good 12AU7s here. Well, I think I'm gonna save that for tomorrow. So thanks a lot for watching the video, and we'll carry on tomorrow with a couple of new or better 12AU7s. Hopefully I've got some. See ya.